Alright folks, we're going to go ahead and continue with another lecture. We're going to talk here for a little while about observations, and to get you hopefully a little more motivated to make it through, this will take again maybe 10 to 15 minutes, maybe a smidge longer, but this will be the second of two videos this week. We'll start off a little light just to make sure everything's on the same page, the YouTube channel's working, and everyone can access what they need to access. And so when we met on Wednesday, we talked about the idea of observations. How do we understand the weather, and how do we therefore learn how to forecast some of its changes? And that's gathered through observations. Observations are, again, a very critical aspect to what's going on. And so we want to basically get data down near Earth's surface. It's important to know what the temperature is, the pressure. We talked about the number of variables ranging from wind speed and direction, to humidity, to visibility. And the more of this data we can receive, the better. It's also important to receive information aloft. And so we talked briefly the other day about radiosondes, taking these instrumented balloons and sending them up in the atmosphere and trying to gather what's going on well above Earth's surface, still mainly within the troposphere, and using that to help us get a better handle on the three-dimensional picture and therefore be able to make better predictions of what might happen in the weather. We're going to do our best. I'm trying to think logistically how this might work to launch a weather balloon. It's possible that I make it an optional activity sometime next week in between classes. It's possible that we do try to do one during the class, and we will figure out how to do it properly distanced. It is something that we can do. We just got to be a little careful about things. If we don't do it, we'll still be fine in the class. It's just kind of one of those fun hands-on activities that helps you get engaged with what we're learning about a little bit better. But again, it's 2020. Life never works out the way that we want it to this year, and so we'll just kind of put that on the burner and see what we can make of it. So we have surface stations. We have a station next time you're walking by Urschel Hall, kind of on the north side of the parking lot, maybe a blue Dodge Ram truck sitting near it. That is an instrumented tower that was put in about a decade ago and reads anything from temperature to pressure to even how much solar insolation is reaching Earth's surface and what's known as a pyranometer. No, you do not need to know what a pyranometer is to do well in this class, but you can, if interested, take a class if you continue in meteorology called instrumentation, which will teach you a lot about things even such as pyranometers. We have another feature on top of Calais Christopher Hall that you might be able to see if you're walking from Urschel Hall, and that is our weather bug tower. That was put there a number of years ago. It was actually sponsored by WGN TV in Chicago, so if you've ever watched Tom Skilling or some of the other meteorologists there, we were contacted by a gentleman there and said, hey, we'd love to do this. It gives them some exclusive rights to our data within the Chicagoland area. But we do have a camera even there, kind of points out towards the circle, the roundabout there over by Dairy Queen. And then we have other ways of getting information around campus. We do have, of course, Valparaiso International Airport, where am I going there? Valparaiso Regional Airport, just to the east of campus. That is, unfortunately, at the time of this video, still down, as we'll see in a moment. But still some pretty interesting stuff that's going on over there. So thermometers measuring temperature, barometers measuring pressure, anemometers, wind, rain gauges, rain, shock, solometers, how high are the clouds, important for things like aviation. We launched the radiosondes, basically a balloon that takes a package that can read some data such as pressure, temperature, and wind, or we can, well, if we're up in an aircraft, instead of putting them with a balloon, we can drop them down to Earth's surface. And so if you've ever seen on the news the hurricane hunters that will go and try to investigate what's going on in the tropics. Side note, we might be able to talk a little bit about the tropics when we meet on Monday, because there's some pretty interesting possibilities going on in multiple locations. But there they'll fly at a decent altitude, and they'll basically have a chute to where they can send one of these tubes down and gather data as it descends towards the surface. Radar gets us data for a large area in a pretty small amount of time. And then satellites, very critical, as we mentioned, the fact that we can get data in areas that people don't exist and at temporal resolutions that were many years unthinkable. Pretty fascinating stuff in many ways. And so here are what's known as the Automated Surface Observing Systems, or the ASOS network. Many of them are sponsored by the National Weather Service or their Federal Aviation Administration, but you can see there's a handful of other from Department of Defense type setups. You can look near Chicagoland and see a handful of them, and you can see one near Valparaiso. The KVPZ airport, which is not international, is again an official ASOS site. And so that's important data that gets fed right back to the National Weather Service. It is publicly accessible, but is one of the official sites. There's going to be a number of them you see. WeatherBug, for instance, they're not official. They're oftentimes placed in areas that don't get good readings. We don't spend time talking about what's important when you cite a tower, but you don't want to put it near buildings and things like that that can absorb heat or change the wind direction from what would otherwise be natural. And so there is the ASOS over at KVPZ down at the bottom. Actually, that's just a standard one in the upper right. You can see some things that are well above Earth's surface. For instance, we measure the wind up at around 33 feet or 10 meters. Other things such as temperature are closer to the surface. We have other sensors here which are measuring things such as visibility and precipitation. We see this feature down here that kind of looks like a mailbox, and that's actually pointing a laser upward and trying to determine where the cloud heights are located. Group down at the bottom, kind of a goofy looking group, is a bunch of meteorology majors from a few years back that I took over to the airport, and we were able to see the ASOS up close. And well, I guess if you're a meteorology student and you see an ASOS, you might as well get a group selfie intact. And so at the bottom, you can feel free to click on the KVPZ ASOS link if you're following these slides that'll also be posted on the Blackboard website. So I'm going to go ahead and bring this up here in a moment, if I can click on the right link. And of course, we're not getting things the proper way, so we're going to try that one more time. And there we go. We can actually see here some of the data that would be taken from the airport. I mentioned in class the other day when we were talking about low temperatures that, well, the ASOS was offline, and unfortunately it's still offline here on Thursday afternoon. So we've had no readings since evening on Tuesday. But here you can see that we have sky conditions again, that salometer, temperature, dew point, relative humidity, and not surprisingly, we don't have any substantial wind chills going on. Pressure, we can measure both in inches of mercury as well as millibars. We kind of talked about that the other day. And so let's go ahead and see if I can't toggle back the right way to our slides. There we go. Radiosondes. There is a network of locations that launch these instrumented weather balloons. One thing that you might note if you're taking a look is, Indiana. We have a total of 0 locations that regularly launch a weather balloon. And by regularly, we launch 2 balloons a day at a number of National Weather Service locations. One occurs in the morning, 0Z, and one occurs in the morning at 12Z, and one occurs in the evening at 0Z. So harken back to your lab that you just finished and that conversion from local time to Z time. So that's going to typically be 6 or 7 in the morning and 6 and 7 at night here in the central time zone. So the closest locations, we got ILX, which is Lincoln, Illinois. We have Davenport out in Iowa, Green Bay, Detroit, and Wilmington near Cincinnati. And if you want to go south, you got to get all the way to BNA, which is Nashville, Tennessee. So once in a while, we will launch weather balloons. This is out on the observation deck. A number of students. We have a PhD here. We have someone who works for AccuWeather here, and a hydrologist with the National Weather Service, another National Weather Service, and believe it or not, yours truly hanging out here in the background. And we will launch these in the weather deck, which is upstairs in this building. And we can get some pretty interesting information that comes back, that vertical profile, which we'll spend a little bit of time talking about now and then over the course of the semester. Satellites. Don't know why that wasn't all up there to begin with. This is a way of remote sensing. We can talk about remote sensing or in situ. In the moment, in the situation, meaning I'm basically holding a thermometer, measuring the temperature, or this idea of remote, something far away taking measurements. And so we will spend a little time now and then talking about satellites. 2 main orbits, geostationary as well as polar orbiting. Geostationary much, much higher above Earth's surface, and the idea that it is stationary in a geographical sense. It's always going to be centered over the same location on Earth's equator. Polar orbits over, shockingly, the poles. And so what that's going to mean at a much lower altitude that we're going to get sometimes better resolution. We're going to get more frequent images of areas that are sometimes distorted pretty heavily by the geostationary satellites. And therefore they're valuable for a number of reasons, and they will supplement what we get with a number of other ways of measuring the atmosphere. Through these satellites, we measure multiple things. Visible, the amount of reflected light. So in other words, depending on whether it's light that's bounced off of a tall cloud versus light that makes it down to Earth's surface and gets absorbed by the Earth, we're going to get different features there. Visible is great if the sun's out. If there's no sun to be reflected, visible imagery is of no use. So what you see here in the upper corner is a visible image. It will give us the most crisp features within the clouds, but again has a significant negative in the sense that it cannot be used at night. Infrared is dealing with emitted infrared radiation. All items, all substances are going to emit radiation that have temperatures above absolute zero, which is, well, everything on planet Earth. We're going to talk more about this next week as well. And so the middle image is going to be an infrared image, colorized enhancement here. And so depending on whether you're near a really warm surface, as might be here over southern Texas and Mexico, you'll get one color. And you see this area between, or I should just say south of Florida, kind of off the Keys, of very bright colors. And that's going to be corresponding to very cold cloud tops, which we would find with thunderstorms. Finally, water vapor imagery. We will spend a little bit of time here and there talking about that as well, looking at how much water vapor exists in certain layers of the atmosphere, which helps us to identify some upper level features such as jet streams. You can get all kinds of things off the satellites. What are the winds like aloft? What is land being used for? Is it crops? Is it simply forest? What is going on with the land? And then also we can measure precipitation, which can be especially helpful when we're dealing with areas that are not in the rain gauge network. And so if I toggle back again here, we can take a look at it, for example, at a College of DuPage satellite. This is going to be off of the College of DuPage web. Should rephrase that again, not a College of DuPage or satellite, but the College of DuPage web page. That's a lot harder to say than I thought it would be. And here we have the water vapor image. And so if I put this in motion, you can see very good resolution by the current network of satellites that we have in Earth's orbiting the Earth. Here you can see again areas that are probably pretty obvious in terms of clouds. You can even see some thunderstorms that are occurring down here in Florida. This would be taken on Thursday afternoon. You can see this area here with this yellowish color, signifying that we have some drier air that's actually moving. And again, you're looking at slightly different areas within Earth's atmosphere as well, so this is not necessarily talking about what's going on down at the surface. Again, looking at geostationary polar, the idea of a geostationary satellite is that it is orbiting over Earth's equator and at a speed that will allow it to stay over the same point on Earth's surface. This is important because then it appears to let the clouds move and we can get a feel for the motion of large-scale systems, individual thunderstorms, or any other type of information. Polar orbiting, again, orbits around the poles. And so that means that with the speed and the altitude at which these are located, each time it comes around the poles and passes over the equator, the Earth is rotated beneath it, and therefore you're getting a different image. What this means is that some areas on Earth do not get the same coverage. You may get images up to a couple times a day, or again, if you're near the polar regions, you get much more frequent imagery. So oftentimes when you're looking at polar imagery, you will supplement that for what's going on in the geostationary sense. Again, we can kind of take a look here. I didn't get that up. Let's see what happens if this pops up properly. Okay, we won't spend the whole minute and 4 seconds looking at this. The idea that your geostationary satellite is going to be set to rotate at a speed that keeps it over the same point. So here you can see, for instance, it's suggesting it's pointing directly over northern South America. And so at all times it's in that same location, which means sometimes it's going to be night, sometimes it will be day. And finally, we'll look at weather radar. Here we're tracking and monitoring precipitation. So we have an image at the bottom there from the Doppler radar, which is on the far west end of campus, behind where they're putting up a new fraternity house and across from Sorority Row. It used to be where the police station was on campus, and so there's an image in the upper right of where that's at. We use radar to track and monitor precipitation. The way it works is that microwave energy is sent out from the radar. Very short bursts of energy are released, and then we simply wait to see what of that gets sent back to the radar. In other words, if I release energy from the radar on a day like, today, and by today that can mean Friday, could mean Saturday, could mean Sunday.
Sometimes getting closer to each other means getting farther away from your routine. Because the best memories are made when you
video and get back to where we were. The beauty of even recording in real time. So here, if there's no precipitation, you're going to see a whole lot of nothing show up on radar. However, if that energy is interacting with anything, a building, don't let that happen, a thunderstorm, it's going to be returned to the radar, and it listens for that echo of reflected energy. When a radar is in use, the vast majority of the time, it's listening for what is coming back. It sends out that pulse and it listens, but it sends these pulses at many, many times each second as it rotates and changes elevations. When we talk about Doppler radar, we're simply talking about the movement of precipitation to be able to tell how is it moving, or even more importantly, what might be going on within an individual storm. Say, for instance, when the radar sees a storm where motions are towards the radar, and very close to it there's motion away from the radar, that may indicate some type of a circulation. This may be even potentially a tornado. Where are these radars located? Relatively good coverage, especially east of the Rockies. You can see there are not a lot of locations, save maybe around northeast Arkansas and the boot heel of Missouri, that are lacking coverage. We are actually kind of equidistant between LOT, which is Romeoville National Weather Service in Chicago, and IWX, which is the Northern Indiana National Weather Service. Typically, we will get better information from LOT in many ways because storms, more often than not, are moving from west to east. We can still get good information from both locations. But you can see as you move out into the Intermountain West, there are many areas that have very poor radar coverage. Admittedly, when you send out pulses from a radar, it will bounce off of anything. That includes mountains, and so it is oftentimes difficult to site these in a location that will be useful. But we can look at things in terms of the National Radar Mosaic, if I can click on the right tab here. And so we can kind of cluster all of what's going on. So this is again taking this afternoon on Thursday. We see a few thunderstorms across Minnesota and the Dakotas. Some activity down there, Florida and the Gulf of Mexico. In fact, if I scroll down, kind of scroll over a little bit, we can see that again, as often happens in the southeast where we have substantial moisture and daytime heating, we get a lot of thunderstorms that scatter about in areas such as Florida, Georgia, and up into the Carolinas. All right, let's wrap this up. Gone a minute or two past where I wanted to be. Read Chapter 1. When I say I went a minute or two past, it's still only going to end up being about 35 minutes of lecture. Read Chapter 1. Make sure we're understanding the difference between weather and climate. Observations. We talked a little bit here in this video in particular about observations and how we understand what's going on in the atmosphere, which is unbelievably critical to being able to understand what is going to happen in the atmosphere. Understand that weather is happening in the troposphere, which is part of the atmosphere, but have a feel for the stratosphere and the mesosphere and the thermosphere as well. And then understand again, how does temperature and pressure behave in the vertical? We realize again, pressure is very simple. It always decreases as you go up, but temperature can be a little different depending on what is going on at your location in the atmosphere. That is all for this Friday. Again, 2 videos. Some information will be sent out. We'll get some feedback and we'll continue to do this for some upcoming Fridays. Hopefully this allows you a pause in your schedule and is a good way of getting some delivery. Take care, and we will see you on Monday.